Hi, I'm Alan Schaefer, Apple's graphics evangelist. The iPhone SDK has a lot to offer for graphics and media developers, with frameworks for mobile 2D and 3D graphics, for animation of your user interface, for handling images, audio playback and recording, and for video playback. And many of these are APIs you may already be familiar with on macOS 10. But now you can take advantage of all these capabilities in a game or application that you write for the iPhone. In this presentation, I'm going to cover 6 of the graphics and media APIs provided in the iPhone SDK. I'll start with UIKit. This is the high-level framework used to create your application's user interface, but it has a few classes built in to handle some basic 2D graphics tasks. Then Quartz 2D, which is the low-level 2D drawing engine, and Core Animation, which is a 2D compositing system with an implicit animation engine, something you see in use all over and in the built-in applications. Then OpenGL ES, particularly for you game developers. This is the mobile version of the 3D graphics standard used on our desktop systems. The new Media Player framework, which handles movie playback. And finally, Core Audio and OpenAL, which lets you play sounds or record audio in your application. So let's start with a few of the classes you'll find in UIKit. UIKit is a library of classes used to develop your application's user interface. It's a very rich API, and it provides things like views to draw into, and buttons and labels, and scrolling lists, and event handling, and so on. And it's covered in more detail in the application frameworks overview. But at this level, there are some graphics operations that are very common, things like drawing images and setting colors or filling rectangles. Also, UIKit provides a high-level interface to animate your UI components. Many of them have elements with properties that can be animated to move or scale or rotate, fade in, fade out, and you can have animated transitions from one view to another or one screen to another. Now, if you need to go beyond these user interface level graphics, the typical way to do so for 2D graphics is to create your own custom view subclass, override the drawRect routine, and dive down into Quartz. For 3D graphics, you'd set up a core animation layer and render into it with OpenGL ES, which I'll cover in a moment. But in either case, you'll still use UI screen and UI view methods to provide you with the screen and context hooks you'll need. Now let's look at a few of the classes you'll use for graphics in UIKit. The UI image is for manipulating image data. You use this class to load images or create new ones and draw them into a view. There's also a UI image view class, which is very simple. It puts an image on your interface, or you can set it up to animate a slideshow of images. UI color holds an RGB color. Fonts and labels are used to put text on your interface. And the UI screen will give you back information about your screen dimensions. And finally, there's a number of utility functions to draw simple shapes like rectangles, functions to output particular image formats, and the hooks used by the lower level frameworks to get screen info and a context to render into. That's a quick view of graphics in the highest level framework, UIKit. Next, let's look at Quartz 2D. So the core graphics framework is the 2D drawing engine. This API is the workhorse for drawing vector graphics, for drawing lines and shapes, patterns, gradients, text, images, and even PDFs. It's a low-level procedural API used heavily by the higher-level frameworks like UIKit. So let's quickly walk through some of the fundamentals of core graphics. First are the basic primitives, points, lines, and rectangles. These are the building blocks for the rest of core graphics. In addition, points are the building blocks for creating paths. Paths let you define arbitrary shapes, and these can be lines, strokes, and curves, or if it's a closed path, you can draw filled shapes. That filled shape can have a solid color, or there's routines to draw gradients, either radial or linear. Core Graphics also provides the low-level engine for drawing images. The iPhone SDK supports a number of different image formats listed here, but PNG is the recommended format. You should convert all the images in your application bundle to PNG for best performance. And finally, Core Graphics has extensive functionality for working with PDFs. It can read, parse, annotate, and write PDF files. Now, let's sidestep a moment. So Core Graphics is a state machine. So besides the actual drawing primitives themselves, there's also a number of graphics state elements that control how each primitive is drawn. You set the colors for strokes and fills. You define coordinate space transformations and other details for drawing style, opacity, shadows, blending, and so on. Another basic concept to understand in core graphics is that drawing order matters. It uses a painter's model, which means the graphics are always painted over whatever was there previously. For example, you start here with a blank canvas, and then you draw this gradient. Then you draw the image, and all the parts of the gradient where the image is drawn are replaced. Then you add this semi-transparent graphic, which is blended, and this logo to create the final result. If you had drawn in a different order, you'd get a different result. So let's take a look at what core graphics code looks like. Here we're in a drawRect method of our custom view subclass, and we ask UIKit for a handle to the current CG context. The context has a coordinate system defined as part of its graphics state. The lines and grid here are just for illustration purposes. They're not actually drawn on the device. But note that since we got our CG context from UIKit, it follows the UIKit convention, where the origin is at the upper left-hand corner of the screen. So we define a rectangle with CG RectMake, and we're saying the origin's at 4040 and the dimensions are 240 by 120. We set a fill color, the values are RGBA, so we're setting it to blue, fully opaque, and we fill the rectangle. This draws it into our context. And here's how it looks. We get a blue rectangle. And in the next step, we're going to use that same rectangle to draw an outline. In core graphics, that's called a stroke, and here we set the stroke color to green. Then make a call to draw the outline of width 10 into our context. And here's the result, a blue rectangle with a green outline on top. So that was a quick look at Quartz 2D. Now let's move on to core animation. So core animation is amazing. It's the framework underlying all the animation in the built-in applications. It's how we smoothly transition from view to view, from screen to screen, or one application to another. It's how user interface elements slide into place instead of just appearing out of nowhere, and that smooth interaction is a big part of the appeal of the iPhone. So you should think about how animation can enhance the user experience in your application. Use it to add realism and provide feedback, and to convey state changes and smooth out the transitions in your interface. There's two overall concepts in core animation to learn about: layers and animation. Layers are the building blocks, and their contents are composited on top of other layers. Then an implicit animation engine animates the layers. And core animation follows a very simple programming model. You just tell it where you want something to end up, and that's all. There's no need for you to calculate any of the step-by-step animation. The implementation takes care of animating that object to its destination or that property to its new value. Now, I'll point out, if you're just using UIKit, there are a lot of classes with properties that are animatable. And for those, you don't need to learn core animation. You can just use the UIKit APIs, and it'll use core animation itself. But let's dive deeper into the main concepts of core animation. I'll start with, what are layers? Well, they're a flat surface drawn in a 3D space. So here's an example. Say you have a photo as the contents of a layer. Then you have some text in another layer that you're going to overlay on the first one. Then you have some graphics in a third layer to go on top. Now, the vertical separation here is just for illustration purposes. When these layers are actually drawn by the system, they'll be composited together. And here's another example from the Photos app on the iPhone. You'll have to watch carefully, but you can see several layers here. The photo covers the whole screen. That's a UI image view drawn into a layer. Then there are some semi-transparent bars that appear at the top and the bottom. Those are individual layers with a label or various controls drawn into them. But now let's slow things down and see what makes layers so interesting. It's the animation. So watch as the user brings up the controls. You can see this layer sliding up into place and then animating out of the way again. You can see the layers at the top and bottom fading in. Now, after the user adjusts the photo, this new layer with a status message appears and fades away when it's done. Take one more look here at the layer on the bottom. After the wallpaper has been set, this layer fades out and its replacement fades in. It's a different size and shape, different controls, but it's all a seamless experience. So now that you've seen layers and animation, let me introduce you to some of the main classes. CA layer is, of course, the main class, and all these properties you see here, the contents, bounds, positions, opacity, and so on, are the specific elements that can be animated. If you animate the contents, you'll get a transition effect. If you animate the bounds, you'll get a scale effect. And if you animate the opacity, you'll see the layer fade in or fade out. Then there are a few specialized layer classes. The EAGL layer in particular is for rendering in OpenGL ES. The tiled layer is to be able to represent multi-resolution content in a layer, and the scroll layer is for scrolling content. On the animation side, a basic animation is one that goes from one value to another value by some increment. So this is from point A to point B. The next kind is a keyframe animation, which is in essence point A to B to C to D and so on. It has a list of values instead of just two, and perhaps a particular path that would follow between each of them, and various ways to change the timing along the way. The next kind is a transition, to go from what you see in one state to what you see in a different state. And finally, an animation group, so animations subject to the same timing can be grouped together. So check out the samples and documentation for these classes, and you'll be up and running in Core Animation in no time. But now let's move on to OpenGL ES. OpenGL ES is the interface for high-performance 3D graphics on the iPhone. It's the mobile variant of the OpenGL standard. The iPhone SDK supports OpenGL ES 1.1, which roughly correlates to the fixed function pipeline in OpenGL 1.5. The OpenGL ES API is, for the most part, a subset of the OpenGL API on the desktop. So it's easiest to learn OpenGL ES in terms of the differences. And a lot of these come from its design goals. The first goal is to be efficient. So over the years, the desktop version of OpenGL has collected at least 6 different ways to submit vertex data to the GPU. So there is no need to bring all that redundancy over to OpenGL ES. Instead, the most efficient techniques, vertex arrays and VBOs, are the only ones supported. The second goal is to be compact, which reduces the memory footprint of the implementation. For example, there's 32 different ways to set a color in desktop OpenGL, depending on if you're using an int, a float, 2-component, 3-component, and so on. And OpenGL ES reduces that number to 3. The third goal was to pare down modes that required extraneous work to take place in the driver, when the programmer could have just chosen a better approach. So OpenGL ES supports points, lines, and triangles, but not quads and polygons, because the driver would just convert those into triangles anyways. It uses GL read pixels formats that don't require swizzling. Now, in spite of these design differences, the fact is that OpenGL ES and OpenGL on the desktop share the same key concepts and most of the same API. There's still per vertex operations and primitive assembly. There's still transformations, pixel operations, rasterization, per fragment operations, and whole frame buffer operations. There's also some extensions which are really useful and particularly targeted to game developers. Matrix palette is used for vertex skinning on a character. Draw texture provides a fast 2D texture blit, and point size array is used for particle effects like smoke, fire, water, and so on. So for the precise comparison of OpenGL ES to desktop OpenGL, just visit the Khronos website. The spec is there, and it lists every function, every parameter, every enum, and tells you whether or not it's available in OpenGL ES. So check it out. It's at khronos.org/OpenGL ES. All right, so that was a quick look at OpenGL ES, and next up is the Media Player Framework. The Media Player Framework provides the facility for full-screen video playback. Movie files can be loaded from your application bundle. For example, if you're using a short clip with animation as a bumper between levels in a game, or they can be downloaded from the network. Now, video automatically expands to play full screen. The movie controller presents the movie on top of your application's content. And if the movie has a different aspect ratio than the screen, you're able to apply scaling to decide if it should appear letterboxed or clip. You can also decide whether the user can bring up the transport controls. Movies with extensions .mov, .mp4, .m4v, and .3gp are supported. Now let's look at the API for the movie player controller. You initialize the object by passing a URL to a movie file, and you have methods to play and stop the movie. These properties are the ways to set the scaling mode and enable the transport controls. Then we have these notifications. If the transport controls are visible and the user picks a different scaling mode, you can get a notification for that. And then a very important notification is to let you know when the movie is finished playing. You need this because the play method triggers the movie to start playing asynchronously. Control comes back to your app just as soon as you call that method, so you need some way of knowing when the movie is finished so you can clean up and deallocate the objects. Here's a code sample. It starts out by initializing the movie player controller with the URL that was passed in. We set the scaling mode and disable the transport controls. Now here we're setting up an observer to trigger the notification callback when the movie finishes. We kick off the movie here, and at this point a full screen view animates into place and the movie starts playing asynchronously. Control returns immediately back to us at this point. And then finally, when the movie finishes, our callback is invoked and we can remove the observer and release the object. So that was the media player framework. And finally, let's look at audio. Core Audio is an API for recording, mixing, and playing audio. It has a C interface with very tight integration with the built-in audio hardware on the iPhone and iPod Touch. And audio is an important component for games, but it's also valuable in many general-purpose applications. Now here's a table to show some common audio tasks and the API recommended to accomplish them. First, if your application needs to play a short sound, you should use the Audio Services API. By short, I mean less than 5 seconds. And also, to trigger a vibration on an iPhone, you'd use Audio Services. Now, to play longer audio files, anything more than a few seconds, use the Audio Queue Services API. And a nice thing about Audio Queue Services is that you're not required to hold all your audio data in memory. You just load enough at a time to keep its buffers filled. And to play multiple sounds simultaneously, you should use Audio Queue Services, but there are some important instructions you must follow depending on the formats and how many of the sounds are compressed versus uncompressed. The rule of thumb is if you're playing multiple sounds simultaneously, then no more than one of them should be compressed. But see the programming guide for the details. To record audio, we use the Audio Queue Services API. To stream audio content, use the Audio File Stream Services and then play the file with Audio Queue Services. And for spatial 3D audio, you can use OpenAL. So let's look at a few common operations. To play a short sound, again, something less than 5 seconds, there's 3 steps. First, you'll register the custom sound as a system sound. Then you play that sound ID, and upon calling that function, your sound plays immediately at the current volume level. Unregister it then when it's no longer needed. And a note about the requirements. Linear PCM is the format we recommend for uncompressed audio and IMA4 for compressed. Another common operation, to trigger the vibrate feature on an iPhone, you call that same play system sound function and pass the vibrate token. Finally, I'd like to also mention OpenAL. So OpenAL is a high-level API for 3D spatial audio, and is particularly targeted to game developers, and it's designed to mimic the coding conventions and syntax of OpenGL, but controlling sound, of course, rather than visuals. Now, OpenAL models audio as it would be heard by a single listener in a 3D space. And there's 3 fundamental concepts involved. Buffers are the containers for audio data, each of which can be attached to a source. And sources represent a point in 3D space emitting audio. Now, how a source is heard is determined by its position and orientation relative to the listener. And by creating a number of sources and buffers and a single listener, and then updating the positions and orientations of the sources and listener dynamically, you can present a convincing 3D audio environment. OpenAL is a cross-platform standard, and you can find out more about it at the OpenAL website. And that completes the overview of the graphics and media APIs provided in the iPhone SDK. Of course, I've only barely scratched the surface here, but I hope you're excited by what you've seen and want to find out more. The programming guide is a great starting point, and the main repository is developer.apple.com/iPhone. This is where you'll find the programming guides, reference materials for each API, and more orientation videos. You can also contact me. My email address is aschaefer@apple.com, and I'd be happy to help you get started.